Hello everyone, my name is Matthew Anton Lawrence Anyora, and I am from Group 6, in which our group was assigned to report about manufacturing of metals and metal products for constructions. Please bear with me if I have to talk this way because I'm afraid my neighbors would complain about the noise I'm going to create. So I'll try to speak to you in a soft voice, but I'm still hoping that all of you will be able to understand how what I am going to report about, and please bear with me. I would like to apologize beforehand. So, all in all, we have 9 chapters that we are going to discuss, and I am going to discuss to you 2 chapters. The first chapter, which entitles Metal Processing and Manufacturing, and chapter 7, which is the machining processes. So, let's proceed with the first chapter, the metal processing and manufacturing. So, it is generally understood that engineers design products. However, an element of this activity that is often underestimated is the necessity for engineers to design processes capable of making products. Manufacturing is the term used to describe the making of products. The product design and manufacturing disciplines are closely related because consideration of how a component is to be manufactured is often a defining criterion for successful design. The manufacturing discipline has existed in various forms since the Tool Age. Until the 19th century, it was largely an activity reserved for craftsmen. So this was long before engineers were present. And the Industrial Revolution during the second half of the 19th century introduced manufacturing mechanization. The use of machines for spinning and weaving in the textile industry is generally acknowledged to be the beginning of the modern manufacturing. During this time, Bessemer (1855) in England and William Kelly (1857) in the United States proposed methods for the mass production of steel. This was followed by the Hall-Héroult process (1885) for smelting aluminum. These processes provided relatively cheap sources of the materials required to drive the Industrial Revolution. To a large extent, many technological advancements were the result of the availability of new engineering materials. By the end of 19th century, basic machines were available for many rudimentary metal forming operations. Furthermore, the introduction of interchangeable parts allowed machines to be assembled and repaired without the necessity of hand fitting. The development of the manufacturing activity has progressed rapidly during the last 100 years and is now a multidisciplinary process involving design, processing, quality control, planning, marketing, and cost accounting. Materials used in manufacturing. One definition of manufacturing is the conversion of either raw or semi-finished material into finished parts. Such a definition serves to emphasize the importance of materials in manufacturing operations. In fact, the choice of material for a given manufacturing situation may be limiting consideration. In general, a material must satisfy two criteria. First, the relevant mechanical, corrosive, electrical, or physical properties of the material must be sufficient to ensure failure-free performance of the final product. Second, the material should be easy and inexpensive to fabricate. Inexperienced engineers tend to underestimate the importance of the latter requirement, often leading to frustration and redesign. An enormous number of engineering materials are available to the contemporary designer, including a wide range of metals and alloys, plastics, ceramics, and composite materials. It has been estimated that there are over 100,000 choices. Therefore, it is often a difficult decision for the designer to select the best material for a given manufacturing situation. The wealth of information available in this regard should not be either underestimated or hopefully underutilized. It is not the aim. Sorry. So it can see in that table 1.1. It's clear that for many applications, the selection of steel raid is not only the sensible choice, but also the most economical. Nonetheless, the principles developed are reasonably general and can be applied to other materials. So here we can see in your screen, table 1.1, these are the most common materials that is being used in manufacturing. So many other materials have important engineering applications that cannot be effectively served by steel. Often these applications require a specific combination of mechanical properties. So since the late 1950s, the use of polymers has grown tremendously and volume of polymers produced is the second only to that of steel. Many products have been re-engineered to exploit the specific advantages offered by polymers, and many of the manufacturing processes used for metals have somewhat analogous counterparts for plastics, although accommodation for the pronounced viscoelastic nature of plastics is required. So, um, in this table, we can see that iron or steel is the most, how do you call it? Yeah, most number of approximate world production compared to other other metals, and this is because of the time where aerospace applications were um, very much abundant. So the manufacturing of airplanes or spacecrafts during this time was, well, you can remember the Cold War. So that's one of the main reasons for this. Raw materials to finished product. Manufacturing operations can generally be classified into primary and secondary processes. For metals, primary manufacturing usually refers to the conversion of ores into metallic materials. Secondary manufacturing is generally understood to mean the conversion of the products from the primary operation into semi-finished or finished parts. For example, the fabrication of automobile engine blocks from a primary melt of iron or aluminum is said to be secondary manufacturing. It is often difficult to classify particular metal shaping operation as either a primary or secondary process in an absolute sense, as it can be difficult to delineate between the various steps within an integrated manufacturing process. Yeah, so let's proceed with sorry about that. The slides were, I think, they were duplicated. So, okay. Primary manufacturing processes, steel making. So the vast majority of pig iron produced from iron ores is processed by blast furnaces. The evolution of the modern blast furnace can be traced back to the 12th century, and the high carbon of these early furnaces became known as cast iron. Despite these early beginnings, the details of the internal operation of blast surfaces are still not completely understood, partly due to the problem of simulating on a small scale the appropriate operating conditions. Blast furnaces are typically more than 30-meter high and about 10-meter in diameter. The structure is roughly cylindrical and lined with refractory fabric, supported by a water-cooled outer steel shells. A modern blast furnace is shown schematically in Figure 1.1, and we have here the four main ingredients that are charged into the blast furnace to produce pig iron. We have the iron ore, the coke, the limestone, and the hot air. So iron ore is the most commonly used in North America. So the two types of ores that are commonly used are hematite and magnetite. Major deposits of these ores occur in areas surrounding Lake Superior, eastern USA, and in Labrador Trough along the border of Quebec and Labrador. The Scandinavian countries France and Spain, together with Russia, account for the most of the iron ore mined in Europe. Uh, Several other ores used in smaller amounts of commercial steelmaking. Interestingly, one of the most common iron ores are iron pyrite. Uh, it is mined to yield the more valuable elements of copper, nickel, zinc, gold, and silver, often found in association with iron pyrite. Iron is sometimes recovered as a byproduct after separation from the more valuable metals and so forth. So this is the iron ore, this is what you can see in your screen. Next is the coke. So coke is the residual solid product obtained by heating a coal at more than 550 degrees. In the absence of air, driving off all volatile constituents of the coal. It acts as the fuel burning to produce carbon monoxide and to reduce the iron oxide to iron. Coking coal is found in many parts of the world. So this is the coke. Third is the limestone. So limestone is a rock consisting predominantly of calcium carbonate. Within the blast furnace, it combines with impurities in the ore to form a slag, which floats on molten pig iron and is separately tapped into a ladle. Slags consist mostly of the oxides of silicon, aluminum, calcium, and magnesium, and can be used in making concrete as a railroad ballast. And lastly is the hot air. Hot air is the blast is provided to burn the coke. As seen in figure 1.1, which is you can see below, pulverized iron ore, coke, and limestone are admitted to the top of the blast furnace via the skip incline. A preheated air blast is provided to the furnace through a series of nozzles located toward the bottom of the furnace. The furnace operates continuously with a series of complex chemical reactions occurring as the material moves down the shaft of the furnace. So the principal reactions are the burning of the coke to produce carbon monoxide and the subsequent reduction of the ore into pig iron according to the reaction. So this is the reaction. There will be atoms, three molecules or three atoms of carbon monoxide plus iron oxide. I think this is the iron ore, and it will produce iron plus three molecules of carbon monoxide, uh, carbon dioxide. So the byproducts are the carbon dioxide and iron. So Bessemer, the Bessemer converter was developed in the 1850s and provided much of the steel required to drive the Industrial Revolution during the late 1800s. The process consisted of pouring pig iron into a converter mounted horizontally to allow tilting, which you can see later on in figure 1.2. Uh, the principal application for the steel product of the Bessemer process in the late 1800s were the rails for railways, which were far more durable than the cast iron rails they replaced. Excuse me. A drawback of the Bessemer process was nitrogen, picked up by molten metal from the air blast, which can embrittle the steel. So this is the Bessemer converter, in which it was described that it was developed in 1850s and was still used in the later parts of 1800s. So, as the definition suggests, uh, consists of pouring pig iron into a converter that allow tilting. So let's continue. Shortly after the Bessemer process, the open hearth process was developed. An open hearth furnace consists of a shallow refractory lined basin equipped with doors through which the raw materials or charge can be added. A charge consists of measured quantities of pig iron, limestone, iron ore, and scrap metal. Heat is supplied by fossil fuel burners with large generators or checkers that reclaim some waste heat for preheating the combustion air. During the 4 to 10-hour cycle at the operating temperature, the charge is refined through the reduction of the carbon, silicon, and manganese by oxygen contained within the combustion air or additions of iron oxide. Impurities such as sulfur and phosphorus are collected in a slag by reacting with a flux, typically lime. For good quality grades of carbon or low alloy steel with low nitrogen content, which reduces brittleness, can be produced in an open hearth furnace. For this reason, the open hearth furnace accounted for 90% of the steel produced by the middle of the 20th century. However, the size, expense, and long operating cycles of these furnaces have virtually eliminated this process from commercial operation in the Western world, where almost all steel is now produced using basic oxygen and electric arc furnaces. So this is the open hearth steel. So let's continue. The basic oxygen furnace, which you can see later on in figure 1.4, was introduced into commercial operations in the 1950s and now accounts for more than half of total steel production in the Western world. The process consists of blowing oxygen through a molten charge by way of water-cooled lands. During the oxygen blast, the temperature rises rapidly because of the oxidation of carbon to carbon monoxide, which boils through the melt producing a long blue flame exiting the vessel. The oxygen converts some iron back into iron oxide, which immediately reacts with the lime flux and removes sulfur, phosphorus, and other impurities, which end up in the slag. Therefore, the basic oxygen furnaces are usually operated at integrated steel mills consisting of a blast furnace, basic oxygen converters, and associated scrap recycling operations. So this is the cross-section through a basic oxygen steel converter, in which it burns, its temperature rises rapidly as it burns carbon to carbon monoxide. And let's continue. In an electric arc furnace, electric arcs are used to provide heat. This furnace has carbon electrodes that extend through the roof. We can see the illustration of this electric arc furnace in figure 1.5. A three-phase potential of about 40 volts is applied at a high current of about 12,000 ampere. The charge of up to about 200 T usually contains a high portion of steel scrap. A major advantage of the electric arc furnace is the ability to control the chemistry of the slag so that a wide variety of steels can be produced. A large percentage of the steel produced through electric arc furnaces starts out as scrap and therefore does not require pig iron or the associated blast furnace for the charge. This reduces the capital cost of producing molten steel considerably and has led to an increase in the number of so-called mini-mills. So this is a typical electric arc furnace for steel production. And this is an 80T electric arc furnace capable of pouring about 70T of steel every 75 minutes. The cantilevered steel structure above the furnace removes the roof for charging. The open-facing door is for oxygen, carbon, and lime injection during the conversion process. Excuse me, bro. So we were done with the primary manufacturing processes, steel making. Now let's proceed to primary manufacturing processes of aluminum production. Of the metallic engineering materials, aluminum is second only to steel in tonnage. So as if you can recall, table 1.1 could sit there that next to iron is or steel is the aluminum. Aluminum it is the most abundant metallic element in the Earth's crust with sufficient proven reserves to satisfy demand for the foreseeable future. Despite the abundance of aluminum, it does not occur naturally in metallic form and commercial processes, only exists for the refinement of a few aluminum ores. The most important ore is bauxite, which contains about 70% hydrated alumina. Bauxite, bauxite is found in southern France and in subtropical regions, the Caribbean, Australia, and Africa, and is usually recovered by open pit mining. The vast majority of bauxite tonnage is converted into aluminum ore using a combination using a combination of two processes both developed towards the end of 1800s, the Bayer process and Hall-Héroult process. The Bayer process is a series of complex chemical reactions usually carried out on a large-scale continuous basis, which we can see this later on in figure 1.6. To start the bauxite is ground the bauxite is ground to powder and mixed with a solution of caustic soda, the liquor in figure 1.6, and delivered to digesters in which under pressure and temperature up to 270 degrees, a solution of sodium aluminate, water, and red mud develops according to the reaction. So, 2 sodium aluminate, water, and so yep, these are the products of the caustic soda plus bauxite, which will result into sodium aluminate, water, and red mud. The red mud consists mostly of oxides of iron and titanium and other impurities from the bauxite, which settle out of the sodium aluminate solution and are removed. Red mud is a major byproduct of the process with about as much red mud produced as alumina. After removal of the red mud, the sodium aluminate is pumped to precipitators, in which alumina is precipitated by agitation after the addition of seed crystals. The alumina precipitate is filtered and about half returned to the precipitators as seeds to continue the process. The remainder is transferred to rotary kilns or calciners. Calciners operate at temperature of about 1200 degrees and the combined water is removed according to the reaction. So Al2O3 is the alumina and H2O plus heat and can reduce alumina and water. Alumina is converted into metallic aluminum in electrolytic cells referred as pots, many of which are connected in series to form a peptide. So before I forget this flow diagram, this is the flow diagram of the Bayer process for the conversion of bauxite into alumina. So you can see right there the liquor was known to be the, if you can recall, that is the caustic soda is the liquor. So the production of steel and aluminum have been described to give examples of important primary processes. Analogous reduction processes exist for other non-ferrous metals, many of which are based on electrolytic reduction. Although the focus of this text is secondary manufacturing, many integrated manufacturing process operations involve both primary and secondary manufacturing. It is important to appreciate the complexity, diversity, and technology utilized in the primary manufacturing field to, among other things, fully appreciated the integrated manufacturing processes. So this is the diagram and view and side view of electrolytic cell for the reduction of alumina to aluminum. Next, we have the secondary manufacturing. The conversion of primary products into secondary finished or semi-finished components can take place by one of several alternative routes. Many machine parts and metal products can be traced through Figure 1.8, for example. An automotive crankshaft can start out as a primary steel melt and then take shape as secondary casting. Alternatively, it may be forged or built deformation from a primary billet or billet, bar, or metal powder preformed. Regardless of the technique used to obtain the secondary shape, it is almost always heat-treated and finished machine. So this is the major secondary metal shaping processing routes. And you can see molten metal, there will be shape casting, processing to powder, casting, ingot casting. These are the processes.
Solidification and casting processes. Perhaps the most basic method of metal shaping is to pour a melt of liquid metal into a formed mold to cool into a solid part, namely casting. Casting processes must be well controlled to ensure sound products. This requires appropriate preparation of the liquid and solidification in a quiescent manner. The casting and solidification process involve pouring and cooling the liquid metal. Therefore, in addition to the metallurgical knowledge required to understand the evolution of the microstructure and mechanical properties during casting, a knowledge of the heat transfer and fluid mechanics occurring during pouring and cooling is also necessary. In this chapter, the most common casting processes are described and basic metallurgy, heat transfer, and fluid mechanics principles are introduced to provide a basic understanding of casting processes and mechanism of solidification. There are many casting methods in commercial operation, consistent with the preparation in Chapter 1 and the fact that steel and aluminum alloys are two of the most common engineering metals. The following discussion focuses on these two metal systems. However, many of the processes presented can be applied to other metals and alloys. To simplify the presentation, the most the various methods are grouped into three generic classifications as follows. Ingot casting. The ingot casting of steel and aluminum consists of reducing relatively simple cross-sectional shapes such as 15 centimeter diameter circles or rectangles up to 60 centimeters by 150 centimeter in various lengths. Typically, ingots are less than 10 meters long, weighing in several hundred to several thousands of kilograms. Steel ingots are poured in large molds which are usually tapered to facilitate removal. The molds are commonly made from graphite or blast furnace pig iron. Although the fundamental process of steel casting is relatively straightforward, several issues require special attention. One of these is the control of imperfections and porosity, which may occur during solidification due to the evolution of gases, primarily oxygen, but also hydrogen, carbon dioxide, and so on, dissolved, dissolved with the liquid steel. The degree of gas that evolves results in four generic types of steel ingots. Killed steel is fully deoxidized prior to pouring into the casting mold. The dissolved gases in the liquids still react with the deoxidizing agents that are added to the melt before pouring. The oxidizing agents are typically aluminum, silicon, ferrosilicon, ferromanganese. The oxidizers have a higher affinity for oxygen and for metallic oxides, which flow to the top of the molten bath to form a slag layer. In this manner, when the steel is poured into the mold and solidifies, the concentration of the dissolved gases is sufficiently low that during solidification, gas bubbles or blowholes do not form and an ingot free porosity is produced. A pipe develops due to the solid liquid shrinkage, which is usually removed and discarded prior to further processing. Pipe formation is discussed later in this chapter. Almost all steel grades containing greater than 0.3% C are killed. Semi-killed are partially deoxidized and thus contain some blowholes usually concentrated near the top of the ingot. This is this is because the static pressure exerted by the liquid steel due to gravity prevents porosity formation in the lower half of the ingot. Typically, the volume of the blowholes resulting from gases trapped within the solidified ingot compensate for the shrinkage due to solidification, and consequently, pipe formation is minimized. Therefore, compared to killed steels, the yield is larger, but the quality is lower. Most steels containing between 0.15 and 0.3% C are semi-killed. In a rimmed steel, sufficient deoxidizing agents are added prior to pouring to provide only minimal control over the gas levels. Sufficient gas evolves from the liquid steel after pouring that a strong boiling action or rimming occurs. The gases evolve from blowholes even the bottom half of the ingot. Most steels containing between 0.06 and 0.15 C percent C are rim steel. Rim steels have a desirable characteristics of an outer ingot skin of relatively clean metal. However, this depends on the skill of the steel maker. Cap steels are variants of rim steels. After pouring the metal into the mold, the rimming action is allowed to proceed for about 1 minute, in which at the time a cap is placed over the open end of the mold ingot, essentially stopping the rim action. In this manner, an outer surface relatively free of blowholes is produced. A compen- compositional segregation that occurs in the ingot center is reduced compared to the rimmed ingot. The phenomenon of the compositional segregation is discussed later in this chapter. This process is particularly advantageous for steel with greater than 0.15% C. Aluminum ingots are scat are cast aluminum ingots are cast using the direct chill process shown schematically in DC casting. The aluminum is poured into a shallow water cooled mold. When the metal begins to solidify, the starter block is lowered at a controlled rate, typically about 9 centimeters per minute, and water is sprayed onto the surface of the freshly solidified metal as it exits the mold. In this manner, the outer periphery of the ingot is solidified by heat transfer through mold, while the bulk of the ingot is solidified by the water spraying of the outer ingot surface. Typically, several ingots will be cast simultaneously from one stream of molten aluminum. The disadvantage of direct chill casting is that the outer layer has a different metallurgical structure than the inner regions because the difference in solidification rate caused by the two-step cooling, consequently, the surface layers of the ingot must be scalped or machined away prior to further processing. This advantage can be eliminated by the water-cooled mold is replaced with electromagnetic field that produces horizontal forces which hold the liquid aluminum in place. This, elimin- this eliminates the mold and the formation of an outer efficiency. Excellent control of all pouring and casting parameters are necessary with electromagnetic casting, but the improved quality of the ingot produced has its favorite technique for the production of high quality aluminum products such as ingots that eventually end up as beverage cans. Cast ingots almost always processed into a semi-fabricated product such as coils, forging preforms, extrusion, and etc. Using of the bulk deformation process outlined in chapter 4. Continuous casting. The casting of ingots is usually in batch process that produces large section requiring substantial subsequent processing. Large mechanical equipment that has high construction and operational costs are necessary to break down most ingots to ferrous and non-ferrous metals. With much smaller cross-sectional shapes can be produced directly from the liquid metal with a continuous casting process, thereby eliminating the handling and processing problems associated with large ingots. The benefits of continuous castings were identified by Sir Henry with Bessemer, but it took nearly 100 years to overcome the various technical difficulties before there was any significant commercialization. The equipment arrangement of the continuous casting of steel varies depending on the product to be produced, be it slab, bar, rod. Is the arrange It is the arrangement for the continuous casting of slab. Although an advantage of continuous casting is a reduction in the size of the equipment required. Compared to ingot casting, still continuous casting operations are still large in scale, with the total height of the equipment typically about 30 meters. The continuous casting operation begins by hoisting a ladle of appropriately treated liquid steel to the top of the works through a stopper arrangement in the bottom of the ladle. The steel is poured into a tundish. The tundish serves as a reservoir in which the steel resides for about 10 minutes. This allows empty ladles to be replaced without stopping the casting process and helps to improve the steel quality as impurities flow to the top of the tundish, forming a slag. A steady stream of molten metal flows after the bottom of the tundish into a water-cooled copper mold that has a cross-sectional shape of the strand to be cast. As the metal passes through the mold, sufficient heat is removed so that the outer periphery of the strand is solidified. After exiting the mold, multiple water jets play into the strand to solidify its core. Once solidification is complete, various pinch rolls, straighteners, and other such equipment are used to control the movement of the solid strand. It is then reheated and cut into manageable lengths of 6 to 12 meters. The solid strand is usually curved from a vertical to horizontal orientation to save space in the works. Control of the process is essential. If the primary cooling of the strand by the mold is inadequate, or if metal is passed through the mold too quickly, the outer periphery will not solidify enough to retain the stale liquid core. In such circumstance, The liquid core can break out to a substantial pressure head and spill over the adjacent equipment, causing expensive damage and safety hazard. The continuous casting is capable of producing a slab shaped strand up to 25 centimeter thick and nearly 200 centimeter wide. Nearly 3,000 tons can be cast continually without stopping. Despite the technical challenges of continuous casting steel, the advantages of the techniques have it a popular process. Approximately three-quarters of the steel produced worldwide is now continuous cast. In countries where there is a modern, well-developed steel industry, the percentage is much higher. The commercialization of non-ferrous metal continuous casting preceded the continuous casting of steels as the lower melting temperature of many non-ferrous metals reduce the technical challenges. There are several continuous casting methods for non-ferrous metals, of some of which produce thin strips in widths up to 180 centimeters. One of the more common non-ferrous techniques is the Hazelet caster. In this process, molten metal is introduced between two mild steel endless belts. The belts move parallel to each other, forming conveyor-like walls. The molten steel is rapidly solidified by water, which is circulated at high velocity in the opposite side of the steel belts. The strip produced is usually delivered to rolling mills that are operated in conjunction with a caster. Hazelite casters are used to produce aluminum, copper, zinc, and lead strip in thickness about 18 to 50 millimeters and up to 100 centimeter in width. Although the economics of producing metal slabs bar strip via continuous casting are favorable. It has not entirely displaced ingot casting. The metallurgy of many alloys is not suitable for continuous casting, and poor mechanical properties can result. In particular, for alloys with a large temperature range continuous in which both liquid and solid phases exit, control of the solidification process is difficult during continuous casting. This problem can be appreciated where it is clear that the solidification is not complete until the location well beyond the mold. Furthermore, when the molten metal first contacts the mold, a thin solid skin forms. However, thermal contraction causes the skin to separate from the mold almost immediately after solidification, and the rate of the heat withdrawal by the mold quickly drops to near zero. This phenomenon can cause major metallurgical and process control problems, which limit the range of the alloys that can be continuously cast. For example, despite extensive efforts, the aluminum alloy widely used for beverage cans cannot be successfully continuously cast to meet the demands of beverage can production. Next is shape casting. Many complex shapes cannot be produced by ingot or continuous casting because of geometrical and economical constraints. Shape casting is often method of choice for manufacturer for complex items such as automotive engine blocks, wheels, and pistons. Such essentially in metal casting, mol- molten metal is poured into a mold that has been formed into the shape part required. Shape casting differs from ingot and continuous casting in that both deformation process are rarely used to achieve the desired geometry. Most shape cast parts require most subsequent finishing, usually the removal of the molten metal, feeding system cleaning, and finish machining of some surfaces. A myriad of shape casting techniques are used to produce a large variety of parts such facilities are much more common than ingot or continuous casting operation. In part, this is because of the relatively low capital cost required for some shape casting and the fact that lower tonnage can be cast economically. Sand casting. Sand casting, the most basic and widely used method of shape casting, has a history of dating back to pre-biblical times, and the name implies sand is used as the mold material. The process has the advantage to lower capital investment, design flexibility, and large alloy section. The major steps involved when sand casting a pipe with an integral flange are are almost dupli- are almost complicated. A split boudin or metal master pattern is made of the shape to be cast. One half of the pattern is positioned from a bottom board, surrounded by a drag bottom of the molding flask. A parting compound, such as talc, is sprinkled over the pattern to facilitate the separation of the pattern from the mold prior to the pouring of the liquid metal. Often, a fine sand is placed against the pattern, and when the cursor of a sand mixture is used to fill the rest of the drag, a fine sand provides a relatively good surface finish on the cast part. The sand is packed tightly to ensure that the shape of the pattern is retained and excess are removed. The drag is inverted to the top half or cope of the mold prepared in the manner of the drag. Permanent mold casting. A disadvantage of sand casting is that the new mold is required for every part cast. Although this may be acceptable where production quantities are small, it is often unacceptable for large scale productions, for which a permanent mold is more suitable in its simplest form. Permanent mold casting involves pouring the metal into a mold that is usually metallic and can be reused many times. This can complicate the mold design considerably and increase the mold cost. Because provisions must be made to remove the casting without breaking the mold, the metallic mold must be made of a metal with a higher melting temperature than the metal being cast. This limits the use of the permanent mold casting process of steels. A major disadvantage of permanent mold casting is the high thermal conductivity of metallic molds compared to sand molds. There are several methods of permanent mold casting, the simplest of which is gravity casting. This process ostensibly the same as sand casting, except that the metallic mold is not broken after each part is made. The metal is poured into the top of the mold and fills it with the assistance of gravity only. The major technical challenge compared to sand casting is designing a reusable mold that permits easy removal of the part. Intensive investment casting. The investment or lost wax casting process produces parts with dimensional tolerance and surface finishes unmatched by other casting processes. This casting technique dates back to Egyptian times when it was used to make ornate bronze bowls and vases. Today, complex shapes such as internal cooled gas turbine blades are manufactured using the investment casting without the requirement of extensive final machining or finishing operations. Indeed, The alloys used for manufacturing gas turbine blades are extremely difficult to machine, which makes investment casting particularly useful for this part. Next in this chapter are certification mechanism. It is clear that the preceding section may that many casting techniques are available for metal certification. However, the fundamental certification mechanism for all casting processes is similar. In the relative short time required for a cast to solidify, the initial micro and macro structure of the part is formed as alluded in the previous sections. This structural element control many of the properties of the casting and the response of subsequent forming operations. Therefore, it is important to understand the metallurgical mechanisms that occur during solidification and cooling. Solidification of pure metals. The solidification of a solid phase from a liquid invariably requires the creation of new surfaces that separate the liquid and solid phase. Energy is required to produce these new surfaces. Therefore, surface energy is associated with the liquid solid interface. This is analogous to the energy associated with grain boundary surface in solid. The energy created the energy create new surfaces requires that the liquid cool below their equilibrium freezing temperature or that they are undercooled before solidification begins. Solidification will occur more spontaneously if there is a high degree of undercooling. The degree of undercooling necessary for solidification is minimized if existing metals are present, which act as nuclei for solid crystals. As such, when a metal is poured into a cooler mold, the mold, the mold walls act as initial nuclei for solidification. In this manner, many small chill crystals are random crystallographic orientations nucleate to the mold walls. To the mold walls. The conduction of heat in the liquid through chill crystals to the cooler mold creates a temperature gradient within the newly formed solid phase. Additionally, the latent heat of solidification is released at the liquid at the solid liquid interface, creating the temperature with a interface temperature above that of both the liquid and solid phases. Consequently, it is conducted away from the interface of the solid as well as the under, undercooled liquid. The steep temperature gradient ahead of the advancing solid phase causes the solid liquid interface to become unstable and protrusions to grow into the liquid. Solidification of alloys. Pure metal solidify at a unique temperature alloys. However, solidify for a range of temperature. For example, the 50 duality percent Cu minus 50 duality percent Ni alloy begins to solidify at 1310 Celsius. The liquidus temperature does not the, the liquidus temperature but does not become fully solid until 1260 Celsius, the solidus temperature. During solidification, the temperature range between the liquidus and solidus is referred to as mushy zones. As the metals in the liquid solid state, proper control of the heat transfer from the solid liquid mushy zone to the casting wall can be difficult, and this can give rise to a number of defects as well as difficulty in controlling the entire solidification process. Difficulties associated with solidification control in the mushy zone regions is the problem that makes continuous casting of alloys with a large mushy zone difficult. or impossible with current technology. Solidification volume shrinkage. As a metal casting solidifies and cools, the volume decreases. The reader may wish to consider why volume of most metals decreases on solidification, whereas the volume of water increases when it changes to ice. There are three major contributions to volume shrinkage: liquid shrinkage, solidification, shrinkage, and solid shrinkage. The amount of shrinkage occurring for a few common metals is listed in Table 2.1. Liquid shrinkage does not cause casting problems as long as sufficient metal is available to fill the shrinkage cavity. To account for solidification shrinkage, the casting pattern must be oversized appropriately and risers added to prevent the formation of shrinkage cavities during solidification. The casting first forms a solid skin at the mold liquid interface as it begins to solidify. This effectively iso- isolates the liquid remaining in the central region of the cube. As this material solidifies, it shrinks and a void forms. Heat transfer during solidification. While the casting is solidifying and cooling, heat is transferred of the metal to the mold. Control of this heat transfer is critical for the production of sound, porous-free casting. In addition, cooling characteristics have a considerable influence on the grain size and microstructure of the cast part, thereby determining the mechanical properties as well as these metallurgical factors. The high heat transfer rates inherent in some casting processes can cause large thermal gradients and stresses. Such thermal stresses may cause unacceptable distortion of the mold during solidification, leading to a poor cast shape. To develop the appreciation of the importance of heat transfer in the casting process, it is advantageous to examine a few basic principles of conductive heat flow. These principles can be demonstrated by considering the simple shape or continuous casting model. Conductive heat flow during shape casting. It is assumed that a metal is solidified against a flat mold surface and an uniform thickness of solid metal forms at all locations. To further simplify the analysis, three more assumptions are made. There is no thermal resistance at the casting mold interface. This assumption is not strictly true for many casting processes, as solidification shrinkage often causes the solidifying metal to pull away from the mold. Number two, no temperature gradient exists within the solid or liquid metal. Again, this assumption simplifies the real physical situation, as there must be a temperature gradient in both the liquid and solid metal, or heat would not transfer. However, as the thermal conductivity of the metal is high compared to the thermal conductivity of the mold, temperature differences in the metal are small compared to those in the mold. Third, the mold is semi-infinite in size and the mold thermal properties are uniform. Also note the assumption of solid planar liquid solid interface means the dendritic formation has been suppressed, although these assumptions obviously simplify the real physical situation. It is evident that the heat flux at any distance in the mold is proportional to the temperature gradient, which may be expressed mathematically. Defects produced during casting. The formation of macroporosity resulting from shrinkage during solidification and cooling has already been identified as a potential problem through judicious sizing and placement of risers. Macroporosity is available in well-engineered shape castings. However, other characteristics of metal solidification can also lead to a number of different types of defects. This section identifies the causes and preventive measures required to avoid such defects. Microporosity, a ramification of a dendritic interface that ha- is that feeding liquid metal to areas between dendrites is difficult. As the metal between each solid dendrite solidifies and cools, it shrinks and unless additional liquid metal can be fed into this region, microporosity forms between dendrites or in the interdendritic regions. At temperatures corresponding to the mushy zone, most liquid metals are very viscous. Therefore, it is often difficult for liquid metal to penetrate and penetrate the complex shaped dendrites, giving rise to the microporosity. In contrast to microporosity occur on a much finer scale and usually has a irregular shape. Microporosity can be avoided by ensuring that the liquid metal velocity in the mold is high. In this manner, the force of the liquid metal flowing against the growing dendrites actually fractures them and they become oriented randomly within casting. This technique results in a equicentric cast microstructure. Although this reduces the occurrence of microporosity, the dendritic structure and microsegregation still remain. Microporosity can be reduced by changing the alloy composition by casting eutectic compositions. Microporosity is most serious when the dendritic arms are long, effectively hindering liquid metal flow. Long dendrites occur when the alloy being cast has a large mushy zone. Since eutectic alloys solidify at one temperature, no mushy zone exists and microporosity is reduced. Gas porosity. Both micro and macro are caused shrinkage during solidification and cooling. In contrast, gas porosity is caused by the absorption of gases into the liquid metal prior to solidification. The most troublesome gas, the most troublesome gas is hydrogen, which usually comes from the moisture in the atmosphere, either natural or as a result of burning fossil fuel for heating and melting. Hydrogen and liquid metal can react according to the relationship. At the high temperature adjacent to the liquid metal surface, molecular hydrogen produced by this reaction decomposes into atomic hydrogen and may be absorbed into solution in the liquid metal. Aspiration. It should be apparent from the preceding section that prior to pouring and casting, considerable effort is directed towards ensuring that the liquid melt is clean and degassed. Therefore, during pouring operation, it is important that the quality of the metal is not compromised. For example, molten metals react quickly with the surrounding atmosphere to produce a surface oxide. This oxide layer often adheres well to the molten metal surface and it serves to protect the underlying metal from further oxide contamination. However, if the metal is not poured in a quiescent manner, the protective oxide can be ingested into the metals and solidified into the casting as non-metallic inclusions. Such inclusions degrade the property of the casting. Often great effort is made to carefully handle the liquid metal for this reason. For instance, in which metal is poured into permeable modes, as in sand casting, atmospheric gases can be introduced to the metal through aspiration. Aspiration occurs when the pressure anywhere in the liquid metal falls below asmo- atmospheric pressure, which often happens in the vertical sprue. For a sprue with vertical walls, air enters metal flow. Consequently, the sprue must be tapered. The taper required to avoid aspiration can be calculated using Bernoulli's equation. Shape casting materials. It is clear that virtually all metals can be cast at some point in their processing history. However, several alloy system has been specifically designed to give good castability and useful mechanical properties. These alloy systems are described in this section. Some of the advantages of eutectic alloys are casting materials that have already been highlighted. The fluidity of these materials is high and the risk of microsegregation and microporosity is lower than for other alloys. In addition, eutectics are low melting point metals requiring less energy for melting. However, alloys that are entirely eutectic often lack toughness. Consequently, many commercial casting materials have near eutectic compositions. These compositions are close enough to the eutectic composition to take advantage of the good casting characteristics, but far enough away to provide sufficient ductile primary phase material for service reasons. Cast iron. Cast iron deserves special attention since it is used more than any other material for shape casting. If, in fact, the tonnage of cast iron used for shape casting is greater than all other materials combined for this purpose. Cast irons have significantly higher carbon content than steels, ranging between 1.7 and 3.5%. Cast irons are produced with four characteristic microstructures. Development of each of these microstructures is explained in the following. White cast iron. White cast iron typically contains 3 to 3.5% C. The microstructure of this material develops during cooling from the liquid phase. At 3% C, white cast iron begins to solidify to austenite at about 1300 Celsius. On reaching 1156 Celsius, the eutectic reaction of L occurs and cinnamite forms at a eutectoid temperature of 727 Celsius. The austenite transforms to with a perlite morphology. Consequently, the final microstructure contains perlite and cinnamite. As cinnamite has a complex crystal structure, plastic, def- plastic deformation via dislocation slip process is very difficult, rendering white cast iron very brittle. However, white cast iron has good abrasion resistance and is used in grinding mills, mining equipment, and rolls for finishing steel, among many applications. Gray cast iron. Gray cast iron is ostensibly the same composition as white cast iron, but is slowly cooled during casting. Slow cooling has a important influence on the microstructure and thus on the mechanical properties. To understand the properties of gray cast iron, it must be realized that cinnamite is not truly equilibrium phase. Given sufficient time, cinnamite will decompose to iron and graphite. This composition is of virtually no importance when considering the metallurgy of steels, which is why the iron carbon phase diagram is usually presented to show cinnamite rather than graphite. Meable cast iron. Meable cast iron is made by heating white cast iron to temperatures in the range of 820 to 1000 Celsius for several days. During this time, cinnamite separates into graphite nodules in a matrix in relatively pure ferrite. Meable cast iron has a good shock resistance and machinability, which improves strength ductility compared to white cast iron. Nodular or ductile cast iron. Nodular or ductile cast iron is a compositional notification of gray cast iron. By adding a small amount of magnesium, the graphite flakes that would normally form develop as graphite nodules. This microstructure offers much better mechanical properties, notable about 15% ductility, which makes this a competitive material with steel for casting craft shanks and other machinery parts. Aluminum cast alloys. The castability of aluminum is greatly influenced by allowing elements that modify the oxide that forms in the surface of molten aluminum, altering altering its fluidity. Silicon is the most important addition in this regard. It improves the fluidity of aluminum, making the cast making the casting of intricate shapes more practical. Furthermore, the SI system exhibits a eutectic reaction at 11.7% Si and 700 577 Celsius, a lower melting temperature than either pure aluminum or silicon. Design of shape casting for manufacturing. It should be evident that shape cast parts must meet all design criteria required of the finished component. However, as mentioned in Chapter 1, it is also important to design components for efficient manufacturing. For shape casting, several design attributes are necessary to ensure acceptable parts are made. A few of these are highlighted below. Draft. Sand casting must be designed so that the pattern may be easily removed of the cope and dragged during the molding of the sand. Pattern allowance. As metal shrinks during solidification and cooling, the pattern must be oversized slightly. Section thickness. It is difficult to force viscous molten metals into long, thin sections. So, because of this, there is a minimum section thickness can be shape cast. This minimum varies depending on the casting technique and alloy. Residual, residual stresses. Different cooling rates within a casting can cause thermal stresses during and cooling residual stresses in the final cast part. Stresses during cooling can sometimes cause cracking of the cast part, a phenomenon referred to as hot cracking. During service, residual stresses may combine with externally applied stresses to increase the effective stress levels, possibly leading to premature failure. Reentrant shapes. Reentrant shapes should be avoided as a mold split at more than one parting line is required. This causes undue complication in the mold design and is easily avoided by altering the shape of the cast part.
And I think that will be all for my part in chapter 1. I'm gonna see you again later in chapter 7, and thank you for listening.
I'm Karen D. Musikalaki, and let's talk about bulk deformation processes. Most metallic materials are subjected to plastic forming. During some parts of the manufacturing cycle, the stress strain principles applicable to all deformation techniques were presented in the previous chapter. However, it is useful to divide the discussion of the industrial deformation processes into two parts: the bulk forming processes and the sheet metal processes. The fundamental difference between these two generic processes is that in bulk forming, the whole volume of the workpiece is deformed, whereas in sheet metal forming, there is only localized plastic deformation, typically involving a change in sheet thickness. The major bulk deformation processes are illustrated in the figure. They include forging, extrusion, drawing, and rolling. The deformation may occur in all regions of the workpiece, concurrently, as in forging, or sequentially, as in rolling, extrusion, or drawing. Rolling is one of the most important bulk deformation techniques. For example, it is used to reduce the cross-section of large ingots or plates which emerge from the ingot or continuous casting technique described at the beginning of chapter 2, for producing a wide variety of finished and semi-finished components. This includes structural steel sections, automotive body sheets, food and beverage container sheet, building sidings, etc. Rolling mills may vary in size from hand-operated units for light gauges of soap metals. to units requiring thousands of horsepower. Several rolling mills configurations are in common usage, two of which are illustrated in the figure. The simplest arrangement is the two-high mill consisting of upper and lower driven rolls between which the workpiece passes. This mill has the advantage of relatively low momentum and therefore can easily reverse direction so that the workpiece can pass back and forth through the mill stand. The four-high mill consists of two driven work rolls with large back rolls that provide increased stiffness. The back rolls prevent the work rolls from bowing due to the rolling pressure which, if not controlled, result in rolled products. Thicker at the center at the edges. For this reason, four high mills are used when the sheet thickness must be controlled accurately. Conceptually, forging is an inherently simple process. As shown in the figure, the three basic types of forging are open die, closed die, and impression forging. It is apparent that open die forging is less suitable for the product of complex finish shape than closed die or impression forging. However, the tooling required is considerably less complicated and expensive. Closed die forging is appropriate for manufacturing complex shape. It does demand close attention to die design and workpiece volume, as it is necessary to achieve complete filing of the forging cavity without generating excessive pressure against the die that may cause it to fracture. Impression forging alleviates this advantage by incorporating flush cutters into the die design to accommodate extra metal or flush not required for the forged part. The major extrusion processes are shown in the figure. Forward extrusion is the most common process and is used for the hot extrusion of both ferrous and non-ferrous metals. In backward extrusion, the movement of the ram is the opposite direction to that of emerging extrusion. In both forward and backward extrusion, the billet material adjacent to the die opening may not be extruded due to friction between the workpiece and the chamber. This results in a dead metal zone which cannot be extruded. The impact extrusion method is often used for the production of collapsible tubes or containers such as spray cans. Drawing. Long products of small cross-sectional area are usually pulled through a die rather than pushed as in extrusion. Such a drawing process is shown in the figure. Drawing is particularly suited for the fabrication of long lengths of small diameter wire with good dimensional accuracy. During drawing, indirect compression causes deformation of the workpiece. That is, the tension applied to the emerging product causes compression against the die face and deforms the metal. To avoid deformation after the wire has emerged from the die, the maximum drawing force that can be applied is limited by the yield strength of the emerging product.
Hi and good day. My name is Hussein Chanjibador and I'll be reporting Chapter 5, which is the sheet forming processes. So let us know what the sheet forming processes is. So basically, sheet forming processes is a process where pieces of sheet metal are modified to its geometry rather than removing any materials. So in a large measure, the importance of sheet forming is due to the availability of high quality and relatively low cost flat rolled metal strip. Conversely, the importance of sheet forming underlines the importance of the rolling process discussed in the previous chapter. Typically, sheet metal is produced by high-speed cold rolling of coils, which may weigh from several kilograms to several thousands of tons. The subsequent localized deformation of the cold rolled strip by sheet metal working techniques produces many useful shapes, such as the car body parts, food or beverage containers, window screen frames, and countless other products. This chapter introduces the most common sheet forming operations. So I will be discussing the most common sheet forming operations one by one. The first is the formability. So by definition, formability is a measure of relatively ease with which a metal can be plastically deformed. So in other words, it is a degree of deformation that can be achieved in a metal forming processes without creating an undesirable condition. such as cracking, necking, buckling, or a formation of folds and flaws. It is a key attribute for metals intended for sheet forming. The measurement of formability is unfortunately considerably more difficult in the definition. Several formability tests exist, and yet there are relatively few standards. The most relevant tests depending on the process and product interest. A quanti- semi-quantitative measure of formability can be obtained from cupping test, in which most common is the all-silicon test. The general setup of this test is shown in the figure 5.1 and involves deforming the sheets into a cup by a small ball-shaped tool. Here, uh, the height of the cup at the instant that the punch force starts to decrease in the indication of a formability. The decreasing punch forces corresponds to the onset of localized necking. As a failure is associated with local necking, metals with high strain hardening exponents and usually exhibits better formability in addition to localized necking. Poor formability may cause several undesirable surface features. This includes orange peel or stature or strain marks. Orange peel refers to grainy surface appearance such as surface arises due to the different orientations of individual grains within the polycrystalline metal. So to help us understand what this formability really is, I'll show you a video uh, sample here. So that is formability. So um, the next sheet forming operation is the shearing. So shearing is the shape. Shear is a change of shape without change of volume, a process that cuts stock without the formation of chips or the use of burning or melting or straightforward cutting action between a punch and a die, as shown in figure below. Also, basically, shearing is like cutting. So in A, this is the general arrangement of tooling for shearing. So then he does had money initial cutting occurring by plastic deformation. So ga paano siya ga sugod na siya shear. So sa C, shearing during punch penetration. Kani dayon fracture following shearing and mo na siyang result. So basically ang shearing mo ra siya gakat og metal strips or metal depending sa kuan sa iyang thickness. So an important shearing operation is slitting of flat rolled sheets into narrower widths. Slitting machines as shown in figure 5.4 utilize rotating slitting knives to shear the sheet at sheet speeds sometimes exceeding 100 km per hour. Open virus, final inspection, and quality control functions are incorporated into a slitting line. So kani siya, mura na siya, gakat siya, pero binulto kani. Mo na siyang sheet lugar. Mo, kuhan man na, anang padulong na dito. Mo din ang finished product, magagat siya sa kuhan, anang different shapes na siya. Ay, dili, different shapes. Different strips na siya. Mo siyang final product. Tapos sa kilid, na mag-cut sa kuhan para ma-control ang width sa sheet metal. So the next is bending. Bending basically is a process in which metal can be deformed by plastically deforming the material and changing its shape. The material is stressed beyond the yield strength but below the ultimate tensile strength. So sa bending, kuan man siya kanang mas siyang more self-explanatory. The material is just beyond the yields but below ultimate tensile strength. Tensile strength. Gabend siya para beyond siya sa yield strength pero below sa ultimate tensile strength para dili pag bend dili siya makuan maputol or bali inhan ito. Mas siyang figure above illustrate the press brake step necessary to fabricate a closed back section by repositioning the die and changing the punch line. Mas siyang step sa pagkuan paghimog rectangular sections 7 steps. First step mo siyang anang straight line nga kuan metal strip. Pagka step 2 mo na din balhin din siya dinhi para ma-form ang first nga kuan ani so on and so forth. So mo ni siya sa test 7 nakahimo na siya kuan rectangular shape per anang gamit ang kuan metal strip. So in bending this is important part of bending, the spinning. Spinning is quite unique from bending. The operation often proceeds at a relatively high speed and is most suitable for making simple axisymmetric shapes such as bows and light reflectors, but it can utilize to manufacture complex shapes. I have a video for spinning to help us understand what it really is. So, mo to siyang spinning, murag po siya katong murag woodcraft instead sa wood kuan siya metal ang buhat. So the next is stretch forming. Stretch forming is the process referred to as stretch forming is shown in figure 5.10. Essentially, a die is forced against the sheet metal that is firmly held by clamps kani morning die. The shape desired is formed entirely by tensile stretching and limiting strain is that which causes local deformation due to necking. Mo ni siya murag mo ang die mo punch. As mentioned in section 5.2, it follows the materials with high strain hardening exponent N or high strain rate exponent M would have the best stretching formability. More often, the geometry of the stretching operation causes biaxial strains. For such instances, the forming limit is often determined using the punch stretch test, which seen in this figure involves forming in hemispherical dome in test sheet. Prior to testing, the sheet is imprinted with a grid of circles that deform into ellipses. So the next is mo siyang figure 5.11. Mo siya nag-evolve sa forming of hemispherical dome in test sheet. Maragapon siya katong sa formability. Next is deep drawing. Deep drawing is a sheet metal forming processes in which sheet metal blank is gradually drawn into a forming die by the mechanical action of a punch. The process is considered deep drawing when the depth of the drawn part exceeds its diameter. The arrangement shown in figures below is used utilizing a punch, die, and blank holder. Nga siya. Nga siya ginapunch, paubos. Tapos, ah, sa mo ni original deep drawing concept. Mo ni siya ang deep drawing utilizing a blank holder. And kani, deformation zones during deep drawing. So, for example, it is preliminary steps of manufacture of aluminum beverage cans more often. However, the arrangement shown in figure 5.13 and 5.5 figures 5.13 and B5 and 5.13C is used utilizing a punch, die, and blank holder. The workpiece to be formed is usually produced by shearing a cold rolled sheet. Here's a diagram of how deep drawing works. So, muna siya gina-punch paubos. So, to better understand what is deep drawing, I have a video for it. So, mao to siya ang deep drawing uh, deep drawing process. Imagine mura siya ganang simple uh, metal strip na one ato siya na shape due to deep drawing process. So the last is the press working press working of metals. Press working is generally term often used to describe sheet metal forming processes that utilize powered presses with permanent or semi-permanent dies made of tool steels. A common example of press working is the stamping of automobile body components, which are usually made of steel or less often aluminum. The complex shape of many press working operations mean that the workpiece is subjected to a combination of shearing, bending, stretching, and drawing simultaneously. The analysis of such process is quite difficult due to the complex shapes and radically changing geometry with time. Although the preceding section have highlighted the factors controlling these sheet forming processes, the techniques presented do not provide exact solutions for the complicated shapes often encountered in industry. Nevertheless, the principles presented are same ones that applies to the processing of complex shapes. These principles, combined with sound engineering judgment, can provide useful conclusions regarding the suitability of many processing parameters. The information presented in this chapter is intended to provide foundation of knowledge in which sound engineer's judgment required and be based. So that is all for my report, the chapter 5, which is the sheet forming processes. Thank you.
Good day, everyone. I am Riacelo, and for chapter 6, I'm going to discuss all about powder metallurgy. Powder metallurgy is a metal forming process performed by heating compacted metal powders just below their melting points. It is another option for producing specific solid shapes. It involves mixing metallic powders and compacting them in a die. The compacted parts take shape of the die and are then sintered or heated in a controlled atmosphere to metallurgically bond the particles. In this figure, we can see the outline of the powder metallurgical processing steps. To produce metal powder, we have four processes, which is atomization, electrolysis, reduction, and pulverization. Before mixing before mixing it, a lubricant is added, and after mixing, it can then undergo either cold compaction or hot compaction. Atomization, it accounts for the largest production volume. It consists of breaking up a liquid stream of molten metal into fine droplets by the involvement of water or gas jets or by centrifugal force. In this figure, it shows the basic processes of water atomization. Molten metal contained within the tundish flows by gravity through a nozzle and into a high-pressure jets of water that breaks up the molten stream into fine droplets that rapidly solidify and cool within the atomization tank. Reduction of metal oxides. In this process, it uses hydrogen as the reducing agent. The starting material for the pyron process is mill scale, which is crushed and then oxidized in air at 980 degrees Celsius. The resulting iron product is friable and easily crushed to a powder size. In this process, it provides a reducing atmosphere in the combustion gas and introducing into the high temperature flame, and then the metal oxide will be reduced in the form of a fine dust. For the next process, we have pulverization. It is the process of applying an external force to a solid material of a certain size to destroy it and reduce it into fine pieces. The simplest application of this process is the use of tumbler ball mill. In this mill, it contains hardened balls much larger than the powder particles. During rotation of the tumbler, the pulverization occurs by the impact of the hardened balls. The advantage of this process is the ability to produce very fine powders, and for a potential disadvantage of this process is the possible contamination of the powder. This can occur by the transfer of the material from the hardened balls to the metallic powder. After the production of metal powders, a lubricant is then added for mixing. And after mixing is powder compaction. Powder compaction is the process of compacting metal powder in a die through the application of high pressures. Powder compaction can occur via cold compaction, and sintering or hot compaction process. Cold compaction. It is the process of compacting metal powder in a die through the application of high pressures. The purpose of cold compaction is to press the powder into a desirable shape. In this figure, it shows the stages of cold compaction. In the first stage, the metal powder is filled within a die, and after that, compaction happens, and it can then form the shape of the die. After pressing the powder, the detail is ejected and is now called a green body. The mechanical strength of the green body is enough to handle it after pressing, but it is not enough to use it in practical situations with increasing loads. The next process is sintering. It refers to the application of heat to the powder compact to increase its strength by bonding together the powder particles. It is also the process of forming a solid mass of material through heat and pressure without melting to the point of liquefaction. This process involves the atoms and materials diffusing across the particle boundaries and fusing together into one piece. In this figure, we can see the sintering process from the metal powder into its final stage. And sintering is also required for increasing cohesiveness and material strength.
Good day, everyone. I am Floyd Castillo in behalf of Mr. Raniera, who is unable to discuss the topic at hand due to unforeseen circumstances. For today, I'm going to discuss about the machining processes. So, as we have learned in the previous reports from my group mates, we have learned that through casting and forming processes, we are able to achieve metal shaping by either through solidification or plastic deformation processes. So, kani siya ng mga processes is the kanang efficient due to the fact na nag-conserve siya sa mass sa workpiece during sa processing. Sige, so mag-make use siya more sa efficiency sa material. However, na siya ay slight nga disadvantage especially sa pag-fabricate og mga more complex na mga shapes or mas nani siya mga dimension ng mga shapes. They are difficult to fabricate using various forming processes, and large parts may require unreasonable forming forces. Even though it's kinda possible, most likely mas mahal siya o most likely dili pag siya mo-work. So, kani siya nga problem overcome through the use of machining. Technically, machining is more costly in terms of raw materials, but can produce complex shapes that will be difficult or otherwise impossible to produce by just casting or forming operations. So, the mga most common na mga machining operations rely sila sa motion between the workpiece and a cutting tool that mechanically removes material in the form chips. So kanina siya mga operations will be discussed later on. The performance of these processes is then influenced by the cutting tool, geometry, workpiece properties, and the cutting fluid. Mechanical machining methods. Most mechanical machining operations are based on the generation of flat or cylindrical surfaces, as these are the simplest to produce. So pag-generate daw nimo og new surfaces, ga-require siya og isa ka workpiece tool that has a relative motion sa duha ka directions. So, in order to reduce the diameter of a bar by turning, we have the primary motion, the cutting speed, represented by V, and the secondary motion, cutting speed, represented by F. So, with these two motions nga, duha motions, with the cutting depth or unsa ka lalo mong pag-cut nimo, there you are then able to produce a transient surface. So, the cutting tool has only one cutting edge. This is referred to as a single point tool. Here we have a figure, relative motions during the turning. Single point machining methods. Single point tools have a relatively simple geometry that contains one major cutting edge, as illustrated. So, the major cutting edge is responsible for forming the chip, which flows past the tool face and generating the transient surface, which passes over the flank. And also, single point tools are usually clamped into a tool post. As you can see in the figure there, the tool is clamped in the tool post. Turning operations most of the turning operations are carried out using a lathe. So the cutting speed derives from rotation of the workpiece, which is clamped by the chuck and rotated by an electrical motor via a gearbox located within the headstock. The cutting feed is supplied by translation of the carriage and tool post assembly along feed rods and driven feed screws. Many machining operations are carried out on a lathe, including cylindrical turning, facing, threading, boring, and more. Here we have a figure of a typical lathe machine with the major components. We also have here a geometry of a cylindrical turning in A and B in facing on a lathe. Planing and shaping. So planing and shaping are both single point metal cutting operations with linear primary cutting motions. So shaping is useful for relatively small workpieces. So for smaller workpieces, shaping is preferred. However, for the larger components, it requires an excessive ram stroke, which reduces the accuracy with which the tool can be positioned. Therefore, for the larger workpieces, it is preferred to use planing rather than shaping. During planing, the workpiece is clamped to a large work table, arranged to provide the primary cutting motion. Here is an illustration of a machine arrangement for shaping. And this is the machine arrangement for planing. For planing, the primary cutting action is generated by workpiece motion, whereas for shaping, the primary cutting action is generated by tool motion. Next, we have multiple point machining methods. So unlike the one we discussed earlier, a multiple point tool has more than one cutting edge. To incorporate the multiple cutting edges, these tools typically have a more complex geometry than single point tools, and therefore are much more expensive than a single point tool. So in this section, three of the most common multiple point machining methods, the drilling, milling, and grinding, are described. Drilling, so it is probably the most common one out of the one we're discussing today. Drilling is used to create round holes in a workpiece. The primary cutting motion is the drill bit rotation, while the feed motion is the movement of the drill bit along its axis of rotation into the workpiece. Next is milling. Milling machines are capable of producing a wide range of cut geometries, including flat surfaces, angles, gear teeth, and slotting. The tool consists of multiple cutting edges arranged around an axis. The primary cutting action is produced by rotation of the tool and the feed by motion of the workpiece. Milling machines with a vertical spindle are also available. As also similar to the previous operations discussed, the workpiece is clamped to a work table and the tool is held on an axis through the spindles. Grinding. Grinding is an abrasive process that removes material by causing accelerated wear of a surface. During grinding operations, the primary cutting motion may be applied to either the workpiece or tool, depending on the geometry. Cutting fluids. So, during sa imong pag-conduct og mga machine operations, there is a tendency nga among tool workpiece, ang iyang friction coefficient o ang iyang interface temperature can be on the higher side. So, meaning ani pagtaas ang temperature o taas ang friction coefficient sa imong tool workpiece, dako kini siya contribution sa iyang pag-wear o iyang pag-corrode. So this is where the cutting fluid comes in. The purpose of applying a cutting fluid is to both reduce the friction and lower the temperature, as well as control the built-up edge, flush away chips, and protect the workpiece and tool from corrosion. Cutting fluids can be classified as either solutions or emulsions. Modern cutting fluids are complex chemical mixtures specifically designed for machining applications. Cutting fluids are most often applied by flooding the tool and workpiece area. So, usay kay tinag several liters per minute ang gina-apply sa kaning mga tools and sa workpiece area. Although most cutting fluids have a low level of toxicity, prolonged exposure of the skin to such fluids can cause a number of minor ailments. So, dili ka siya life-threatening pero still look out especially pag-apply sa cutting fluids. Take precaution. Numerically controlled machining. Numerically controlled machining, or NC machining, extends the machining operations described to include a controller and a numerical data entry device. So, kaning numerically controlled machining is also able to do the same machining operations that were discussed earlier, but it includes na siya controller and a numerical data entry device. So pwede na to siya ma-inputan or ma-control with the use of numbers, letters, or symbols. So it is programmable and can be automated. Numerical control began with the use of metal sheet cards with arrays of punch holes that were used to control weaving machines in the 1800s. The use of NCNC or computer numerical control allows the introduction of sophisticated automation into many metal forming operations. So since it can be automated, mas dali ginapadali na natong trabaho and it can be automated, so less kayo na mas most likely precise siya kaysa sa kung kanang kita ang magamit. Non-traditional machining processes. The widely used conventional machining processes are not capable of producing some geometries or machining several of the very hard, high-strength, temperature-resistant metals. So, kani mga non-traditional machining, it is also called modern machining or non-conventional machining processes. So, instead sa katong mga nandan na to na mga conventional machining process like sharp cutting tool, paggamit sa mga abrasive particles para pag-remove sa materials, magamit ta og various energy forms to as I said, remove material. Kanina mga energy forms may vary. It would include mechanical, electrochemical, thermal energy, chemical energy, so on and so forth. So, the basics of non-traditional machining operations are such as follows: jet machining, ultrasonic machining, electrochemical machining, electric discharge machining, laser beam machining, so on and so forth. So these are just some of the examples. So in comparison, these non-traditional machining processes have lower typically have lower feed rates and require more power consumption when compared to the traditional na mga machining processes. And that would be all for my report, and thank you.
Now let's talk about joining processes. All of the previous chapters have focused on processes that primarily change the shape of individual components. Joining processes differ in that at least two components are joined together, thereby allowing more complicated or larger structures to be fabricated. A wide range of joining techniques are used in various manufacturing operations, including myriad different mechanical fastener, adhesives, welding, brazing, and soldering. The figure classifies some of the major processes associated with each type of joining operation. Several joining operations are more akin to assembly than to metal processing. The major metal processing techniques include welding, brazing, and soldering. A characteristic of these techniques is that the interatomic bonding within the base material, or at least on the surface, is altered, potentially changing the properties of the base material. The control of the base material properties during joining requires special attention to process parameters and as important ramification in terms of serviceability. The essence of torch brazing is the filler metal is heated by a torch concurrently with heating the base metal. The torch burns acetylene, propane, or other gases with air or oxygen, which can be handheld or often separately mounted for mechanized brazing operation. To prevent excessive oxidation of the joint surfaces, the flame is usually adjusted to be slightly reducing. Manual torch brazing is relatively simple and can be mastered quickly by the mechanical adept. Furnace brazing: for relatively high production quantities, it is often more efficient to heat the entire assembly to be brazed in a surface. For furnace brazing, the parts to be brazed must be jigged or clamped together in the desired geometry with the filler metal already in place. The furnace may be a batch type that is capable of brazing multiple components at once, or a continuous furnace can be used for high production rates. Deep brazing: the parts to be joined are dipped into a heated bath of either molten salt or molten brazing filler metal. A major advantage of this technique is fast heating times, which reduce the cycle time for the brazing process. For parts to braze together, they usually must be clamped or jigged to maintain the desired geometry during immersion in the molten bath. A major advantage of deep brazing and furnace brazing compared to torch brazing is that The whole component is heated uniformly, thereby heating distortion. Also, a large number of joint surfaces can be brazed simultaneously. There are a number of welding processes available for joining. These techniques are applied to the structures varying in size for pipelines of several thousand kilometers in length, supertankers and offshore oil platforms, to intermediate-sized structures such as automobiles and railway rolling stock. In addition, many welding techniques are used to produce manufactured assemblies that may not appear to involve welding at all. Welding also has important applications of the repair of structural assemblies. Welding processes are conveniently divided into two classes: fusion welding and solid-state welding. During fusion welding, a portion of the base material to be joined is melted and mixed, often with the addition of a filler metal, forming a solid joint after subsequent solidification. As the name implies, during solid-state welding, the base material is not melted. Joining occurs by a process other than solidification and very often involves diffusional processes. Roll bonding differs from the other solid-state welding processes because it is often used to join much larger workpieces. The process consists of simultaneously apply a large reduction of two sheets by passing them through a rolling mill. As the thickness is reduced, the length increases, creating new unoxidized surfaces that can be bond together. Usually the surfaces are chemically or mechanically cleaned and heated prior to entering the rolling mill to enhance bonding across the containing surfaces. Friction welding. During friction welding, the energy required to join is produced by frictional heating of a rotational part as it is pressed against a stationary part, using equipment of that type. This process is mostly widely used for joining rods or tubes. To generate rapid frictional heating, the rotational speed is high during the initial stage of joining. Pressure welding. Although pressure welding can take several forms, all rely on severe deformation to break up the surface oxide. The basic setup for cold pressure welding, which is not dissimilar to the spot welding, essentially intentors apply local deformation to the metal to be joined, as the two clean sheets are compressed together and form under the pressure of the indentor. The metal floor causes the formation of new unoxidized surfaces that bond together. Ultrasonic welding. High-frequency vibration between two abutting metal surfaces causes localized elastic and plastic deformation of the surface regions when temperature increases as much as 0.5 of the absolute metal temperature. The localized deformation tends to break up the surface oxide, allowing metal contact to occur. Diffusion bonding between the two metal surfaces is enhanced by the increased local temperature. Thermal welding. In some sense, all of the electric arc processes described in the previous section could be considered thermal processes, as all rely on heating to provide fusion. However, it is useful to delineate between the processes that generate heat by electric techniques and those generating heat by other methods. In this latter category, the remaining welding processes, but of particular interest, are gas welding, thermite welding, and the electron beam process. Gas welding involves mixing a combustible gas, mostly often acetylene, and oxygen in a nozzle which is ignited to generate heat. The flame produced is directed into the joint area to provide rapid melting of the base. Acetylene and oxygen are stored in high-pressure cylinder, and therefore the major advantage of the whole process is portability. Without the requirement for an electrical supply, most ferrous and non-ferrous metals can be gas welded, usually with the addition of appropriate filler metal during welding. Thermic welding. In the heat of thermic welding is generated by the exothermic reaction between finely divided powders of a metal oxide, most commonly iron oxide, for welding steels and aluminum. Electron beam welding. The source of heat electron beam welding is strongly focused beam of electrons that have been accelerated to about 60% of the speed of light. This is the same process as described in the electron beam machining. The high power density of the electron beam causes instant melting and vaporization of the base metals. All of the electric arc welding processes rely on the formation of an arc between an electrode and the base material to provide heat. An electric forms when there is an electric discharge between two metal objects that are not in contact with another. In that case, arc welding, the two objects are electrode and base metal workpiece. Shielded manual metal arc welding is widely used for the fabrication of the pressure vessels, pipework and pipeline joints, as well as for the repair and maintenance of the industry machinery. Metal inert cast arc welding differs from the SMA process in several important respects. The electrode of MIG welding takes the form of an uncoated wire, usually the same alloy as the base metal, which is fed to the joint area from coil. The molten pool is protected from the atmosphere by shielding gas delivered to the welding gun under pressure. Tungsten inert cast arc welding. In contrast to MIG welding, tungsten inert cast arc welding involves the use of non-consumable electrode made of tungsten or a tungsten alloy. Submerged arc welding. Submerged arc welding process utilizes an electrode of consumable wire to produce an arc that is submerged below a flux layer. Plasma arc welding. Like the TIG and MIG processes, the plasma arc welding process utilizes an inert gas for shielding a molten weld metal. Unlike TIG, an non-consumable tungsten electrode is used.
Previous chapters introduced various processes aimed at changing the shape of a workpiece. Once these processes have been applied and the final desired geometry is obtained, it is often necessary to alter the properties of the workpiece without changing the geometry to develop the surface performance required. One of the techniques widely used to achieve this objective is the application of heat treatments to modify the microstructure and consequently properties. Virtually all alloys are affected by heat treatment to some degree. Most heat treatments change the properties of the workpiece throughout. However, it is sometimes desirable to only modify the surface of the workpiece to improve wear resistance. Often, an advantage of only modifying the surface is that a tough, pressure-resistant microstructure can be retained in the bulk of the workpiece. Once a hard wear-resistant surface is obtained, consequently, it is not uncommon to apply heat treatment that will provide sufficient strength and toughness throughout the part and then apply a surface modification process to impact wear resistance. Wear is damage involving progressive loss of material due to relative motion within a surface and a contacting substance. There are four tribological systems: smooth solid sliding on smooth solids, hard, sharp substance sliding on softer surfaces, surface fatigue caused by repeated stressing, and relative motion between fluids, possibly with suspended solids and a solid surface. The variety of techniques to reduce wear rate caused by these tribological systems can be briefly summarized as: separate the containing surfaces with a lubricant film. Second is choose material combinations that are resistant to sliding interaction. Third is harden the wearing surface. Fourth is improve the resistance to fracture of a wearing surface. Fifth is improve the corrosion resistance of an eroding surface. Sixth is improving the fatigue resistance of a wear surface. Types of wear. Abrasion is a result of hard particles forced against a solid surface with relative motion. During low-stress abrasion, damaging hard particles are not deformed, as is the case for high-stress abrasion. Examples of low-stress abrasion particles sliding on chutes, plowing soil, and or degrading operations. Gouging abrasion often occurs concurrently with low and high stress abrasions as a result of compressive loading striking the wearing surface. Polishing wear is the unintentional removal of material caused by rubbing without visible scratching. Posi- Polishing is closely associated with low stress abrasions, and both mechanisms can occur concurrently. Erosion. Erosion is the gradual loss of the material from a solid surface due to relative motion or mechanical interaction between fluid containing particulate and a solid. Impingement erosion results from a continuous succession of impacts between solid and liquid particles in a solid surface. Usually, this term connotes that the impacting particles are smaller than the solid surface. The impacts cause local plastic deformation of the surface, with each particle causing a small crater and material removal. The rate of impingement wear is proportional to the kinetic energy of the impinging particles and inversely proportional to the hardness of the surface. Many impingement erosion problems exist, such as in the ingestion of dirt and sand by aircraft engines, fans operating in dirty environments, or high-velocity liquid gas flows in piping. Cavitation erosion is caused by the formation of the collapse of bubbles within a liquid near a solid surface. Cavitation results from a decrease in local static pressure as opposed to boiling, is which is caused by increasing temperature. Cavitation erosion may occur on ships' propellers, pumps, and piping systems, as well as other applications. Slurry erosion is linked to impeachment erosion by fluids. A slurry is a mixture of solid particles in a liquid of a consistency that allows the mixture to be pumped like a liquid. Relative motion of a slurry against a solid surface can cause erosion and can occur in mineral flotation pumps, oil well equipment, cement handling equipment, and etc. Adhesion wear is a progressive loss of materials from a solid surface which is initiated by some form of local bonding between two solid surfaces. If the adhesion wear occurs due to small amplitude of auxiliary motion between the surfaces is termed fretting. The repeated rolling or sliding of surfaces can cause wear by surface fatigue. A common example of surface fatigue is the wear of bearing races in which a wear track develops from repeated contact with rollers or ball bearing. This type of wear can result in pitting, often following subsurface cracking. Pitting can occur in various types of bearings, cams, and gear teeth. Separation of flakes from a surface is referred to as spalling. Spalling is usually more severe than pitting and is often associated with bearing and gear teeth. Thin, hard coatings on a soft substrate are particularly prone to spalling. Diffusional processes. Diffusional surface modification process relies on diffusion of new atoms into the workpiece to alter the mechanical properties of the surface region. Diffusion is the spontaneous movement of atoms to new sites within the metallic crystal structure. When controlled appropriately, diffusions can create a net flux of atomic movement. Although new atoms move into the workpiece, there is no intentional buildup or increase in the workpiece dimensions. Carburizing. The most common of the diffusional surface modification processes is the carburizing of low carbon steels. The objective of carburizing is to obtain a hardware-resistant surface with a tough interior. Low carbon steels are tougher than medium or high carbon steels, but low carbon steels cannot be quench hardened sufficiently to provide good wear resistance. Pack carburizing. is probably the simplest of carburizing processes. Pack carburizing involves placing parts to be hardened on a container filled with suitable carburizing medium, the pack, typically charcoal and hardwood. The pack is to put in a surface and heated into the austenite region of the diagram for a sufficient time to allow the fusion of carbon into component surface. Gas vaporizing is the component heated into the austenite region of the FEC phase diagram in the presence of carbon-containing gas. Typically, the gas atmosphere is methane. Natural gas is approximately 85% methane. Free carbon is available to diffuse into the component by the reaction. As the operation is carried out at high temperature, the potential of a explosion exists. Consequently, atmosphere-tight surfaces furnaces capable of maintaining pressures just above atmospheric pressure to prevent infiltration of air with close control of surface temperature and atmosphere are necessary. Gas vaporizing provides improved control over the case depth and hardness compared to pack vaporizing, and although the labor content is low, more high-skilled personnel are required to maintain the necessary control, the furnace controls. Liquid vaporizing involves the placing of workpiece in a molten salt that contains carbon-bearing compounds, usually the carbon salt, contained within an externally heated metal pot. Most vaporizing salts contain sodium cyanide as active chemical. The salt becomes liquid at 538 degrees Celsius and can be used to temperatures of about 950 degrees Celsius. For diffusion into the workpiece is available for the reaction. Diffusional flow during carburizing. The case depth is controlled by the diffusion of carbon atoms through the surface layers of the workpiece. Carbon from the surrounding atmosphere or pack quickly saturates the sur- surface layer after the start of the case hardening process. The carbon saturation concentration at the surface is the maximum carbon content that can be absorbed in the austenite phase. Nitriding is a case hardening process involving the diffusion of nitrogen into the surface region of steels. Nitrogen can result in surface hardness up to 70 Rockwell C, about 700 ppm, higher than the hardness obtainable by carburizing. Nitrogen diffusion into the surface region of the steel results in the formation of a layered structure consisting of a surface layer of Fe and about 0.1 millimeter thick. Carbon nitriding. Carbon nitriding refers to the process that creates a hardened case by diffusing both carbon and nitrogen into steel. During carbon nitriding, the furnace atmosphere contains about both ammonia and natural gas, and the temperature is typically between 650 degrees Celsius and 885 degrees Celsius. At the lower temperature, most of the hardening will be due to nitrogen diffusion, whereas close to 885 degrees Celsius will cause primarily carbon diffusion. Nitrogen increases the solubility of carbon in the austenite phase and decreases the temperature at which austenite remains stable. Steels are aluminized by coating the surface with a thin layer of aluminum. Aluminiz- um, Aluminizing is somewhat analogous to the zinc galvanizing of both steels. Both aluminized and galvanized steels have improved atmospheric corrosion resistance because both zinc and aluminum are anodic to steel. Therefore, even scratches through the aluminized or galvanized layer does not cause corrosion of the underlying steel. Aluminizing is more effective than galvanizing for elevated temperature applications, and for this reason, many furnace combustion chambers and automotive exhaust components are aluminized, although the latter application is slowly being displaced by ferritic stainless steels. In a manner similar to aluminizing, steels can be siliconized or chromized. Siliconized steels have a surface silicon content of about 13% and exhibit good wear and corrosion resistance in several oxidizing acids. Chromized steels can have a chromium content of as high as 30%. Chromium contents above 12% provide excellent atmospheric corrosion resistance as exemplified by stainless steels. Siliconizing requires heating to about 1010 degrees Celsius and exposing the surface of silicon gas which decomposes, allowing silicon diffusion to form a case of about 1 millimeter thickness. Chromizing is a cementation process which, using chromium powder and a gas such as ammonium iodide at the chromizing temperature of about 1000 degrees Celsius, will react with the chromium powder to form nascent chromium that can diffuse into steel workpiece. Flame hardening. Flame hardening employs the impingement of high temperature flame directly on the workpiece, followed by water quench. Using a oxyacetylene flame, the surface can be heated to the austenite structure in a few seconds. These short heating times ensure that excessive oxidation to the surface does not occur. A variety of shapes for the flame head can be used to obtain uniform heating of complex surfaces such as gears, cams, and shaft. Flame hardening can produce hardened layers of up to 4 millimeters, but the process requires careful control of the flame combustion, the standoff distance of the flame head from the workpiece, and traversing speed. Induction hardening relies of the fact that when a conducting material is placed within a magnetic field, an electrical current is induced in the conductor and this induced current causes heating. Using the principle our Using this principle, our workpiece can be induction heated by making it secondary of an alternating current transformer. The magnetic lines the magnetic lines of flux created by the alternating current at the primary coil cut the workpiece. Of importance is that the induced alternating magnetic flux causes eddy currents to flow within the workpiece. The eddy currents flow in a direction opposite of the inducing the current, and therefore the magnetic field created by the eddy current opposes the induction magnetic field. This reduction is greatest at the center of the workpiece because all of the eddy currents in all the elemental paths are effective in producing opposing magnetic field at the center. Plating processes. Plating refers to the application of metallic coatings to substrates by electrochemical or electrolysis processes. During electrochemical plating or electroplating, the workpiece to plated is made the cathode of an electrolytic cell. On the application of a potential, the anode dissolves into the electrolyte and redeposits on the cathode. When the when controlled properly, an even layer of anode metal adheres evenly to the workpiece. The plating process is governed by Faraday's laws, which are: first, the mass of the substance liberated during electrolysis is proportional to the quantity of electricity passed through the cell, and and the mass of the liberated material is proportional to the atomic weight of the valence ratio. Thin film coatings. Thin film coatings are not applied to the extent of as those surface techniques previously discussed, primarily because of the cost equipment required. However, the use of these types of coating is increasing as the techniques are developed more fully and as greater engineering capability of various components is demanded. Physical vapor deposition. The physical vapor deposition involves evaporation of the coating material in a vacuum chamber by resistance or electron beam heating, followed by condensation of the vapor on the substrate to be coated. But the highest evaporation rate and deposition rate is up to 500 per minute, can be achieved by electron beam heating. Evaporative PVD is used to supply oxidation and erosion resistant coatings on gas turbines blades and vanes. Chemical vapor deposition. Chemical vapor deposition differs from PVD in that it involves chemical decomposition of a gaseous atmosphere and reaction of one of the products of decomposition with substrate surface. The reaction between atmosphere and the substrate causes nucleation and growth of a coating. Often the substrate is heated and the kinetics of the chemical reactions are increased by ultraviolet light or plasma energy sources. Chemical vapor deposition processes exist for many coating substrate combination. One of the earliest CVD processes is the Mundt process for the deposition of Ni coatings from nickel carbonyl.